The next test you have is the integral test for convergence. So far we have the nth term test for divergence. We have the geometric series test, which tells us either convergence or divergence, depending on what our common ratio is. And now we're going to have the integral test for convergence. Oh, we also have partial sums as a tool for telling whether we have convergence or divergence. All right, so the integral test relies on RAM of a function. So as long as you can define your terms as a function that is positive and decreasing, you can approximate your sum by drawing right-hand rectangles under that curve. And so f of 1 would be your first term, f of 2 would be your second term, f of 3 would be your third term, and if you want to add up all of your terms, that's equivalent, that would be less than the integral from 0 to infinity of the function, because these little spaces would be not included in the sum. So we know that the sum is less than the integral, so if the integral exists, then we know that the sum exists. They're not equal, but we know that we can say for sure that the series converges. All right, so let me say that again. We're going to see if we can create a function out of the description of our term, and if that function decreases, then when we draw right-hand rectangles at the integers, we're getting all of our terms, and then if the integral converges, then so does the series, because the integral would be larger than the sum of the areas of all of these rectangles. Okay, so here's the integral test in a more symbolic language. If you write your function so that it's a description of your terms, and it's a continuous, positive, decreasing function, and the integral converges, that's an improper integral, remember, then so does the series. And the integral test actually goes the other way as well. It can prove divergence as well. If the integral diverges, then so does the series. So here's an example. We're going to look and see if this series converges. So this series would be, if we wrote it out, it would be 1 plus 1/4 plus 1/9 plus 1/16. And our instinct tells us, yeah, that probably converges. But here's the proof of it. The proof of it is we know that if I write this as a function, we know that f of x equals 1 over x squared is a positive decreasing function. If you need to prove to yourself that it's decreasing, you could take a first derivative and show that it's negative for x greater than or equal to 1. And the integral from 1 to infinity of 1 over x squared dx would be the limit as b goes to infinity of, the antiderivative there would be negative x to the negative 1. Okay, bye. Oh, I wrote an infinity, but I meant to be. Update, my kid is going to go take a bath. All right, so then if I write this out, I have negative 1 over b minus negative 1. And I'm taking the limit as b goes to infinity, and that goes to 1, so it converges, so yes. And the reason is the integral test. So our first step is we create a function that looks like our definition of our terms, and we prove to ourselves that it's a positive decreasing function for our interval. So I said for x greater than 1 because that's where we started counting for our series. And then we look at that integral and we prove to ourselves that the integral converges. And since the integral converges, we know that this series converges. We don't know that the sum is 1, but we do know that the sum is less than 1 because it's a positive decreasing function. So those left-hand rectangles are going to I'm going to draw a picture. I'm going to show you the picture again. The right-hand rectangles are going to underestimate the function because it's decreasing. All right. I would recommend pausing and trying this one yourself. We're going to check to see if this integral converges. I will do it now, but go ahead and pause so you can try it first. So f of x equals 1 over x. We're going to take the integral from 1 to infinity of 1 over x dx. And the antiderivative of 1 over x would be natural log. I don't need absolute values because I know that I'm going from 1 to infinity, so it's going to be positive no matter what. And then I'm going to do a limit as b goes to infinity of natural log of b minus natural log of 1. And natural log of b, as b goes to infinity, would be infinite. So this one diverges. So that means that this series, 1 plus 1/2 plus 1/3 plus 1/4, which is actually a very famous series, diverges by the integral test. I did skip one important step. Should have convinced myself before I did the integral test that this is a positive decreasing function on the interval from 1 to infinity. And I know the shape of 1 over x from 1 to infinity looks like this, so I know that it's a positive decreasing function. This series, very famous, has a name. It's called a harmonic series. There are several different tests out there to prove that this series diverges, but it does diverge, and we just proved it with the integral test. All right, here's another integral test question. I would recommend pausing and trying it yourself. So I don't know the shape of this one. So if I have f of x equals 1 over x times natural log of x, I don't know the shape, but I do know that as x gets bigger and natural log also gets bigger, so I have a denominator that's getting larger. So I can be sure that this is a positive decreasing function for x greater than or equal to 1. So then I'm going to do the integral from 1 to infinity of that function. And I think this integral is going to require some u substitution. I'm going to make u equal to natural log of x, so then du would be 1 over x dx. So then this becomes great, thanks. I'm going to plug in 1, so I have natural log of 1, which is 0. And then I have natural log of b, and I have 1 over u du. So that antiderivative would be natural log, so natural log of u from 0 to natural log of b, well, that is a mess. So no, this does not converge because natural log of b is going to infinity, so natural log of b would go to infinity, so this diverges. So no good, diverges. All right, one more example. On this one, this is the last example. On this one, we might need a first derivative test to convince ourselves that this diverges, but I could say that as my n is getting larger, my denominator is getting larger faster than my numerator, so I'm pretty sure it's decreasing. So we have f of x equals x, not n, x squared over 2 x cubed plus 2. Isla, do you want to say hi? Hi! Is positive for sure, and decreasing, we're pretty sure, for x greater than or equal to 2. And so then we're going to do the integral from 2 to b as b goes to infinity. And my thought when I see fractions is maybe it's u substitution, maybe it's partial sums, but I can see that if I do a u equal to 2x cubed plus 2, I'm going to get u equal to 6x squared. So I'm going to be able to, du equal to 6x squared. So I'm going to be able to cancel out that x squared. So this would be the limit as b goes to infinity of the integral from, I'm going to plug 2 in, 2 times 8 is 16, plus 2 is 18, and 2b cubed plus 2. And then I have 1/6 over u du. And, oh, it looks like another natural log one. So we have 1/6 of natural log of u from 18 to 2b cubed plus 2. Well, 2b cubed plus 2 is going to go to infinity. Natural log of that would also go to infinity. So no, this does not converge. It diverges by the integral test. All right. So integral test. You got to show that you have a positive decreasing function. You can usually just convince yourself of that, but take a minute and think about it. Then you do the integral, and you check to see if the integral converges to a number. If it diverges, so does your series. And if it converges, then so does your series. All right, good luck, have fun.